Welcome to this explainer. Today, we're jumping right into a seriously fascinating Haskell refactoring journey. We're looking at a complete code makeover, one that takes a messy, defensive, and frankly exhausting code base and transforms it into a clean, self-enforcing masterpiece. If you've ever felt like you're constantly writing boilerplate just to protect your program from scenarios that shouldn't even exist in reality, you are absolutely going to love this. Let's get right to it.
So we're talking about making illegal states unrepresentable. It's basically the holy grail of functional programming and type-driven design. But what does that actually mean for us? Well, it means leaning so heavily on your language's type system that if a piece of data is logically impossible in the real world, it's physically impossible to compile in your code. The compiler essentially becomes your bouncer, kicking out bad logic before it ever gets a chance to run.
Here's our roadmap for the makeover today. We're going to tackle the impossible state problem, fix up the block data, rip out those optional types, watch the codebase magically shrink, and finally fully leverage that type system.
Starting with Section 1, the impossible state problem. This is exactly what happens when your code allows the impossible. Let's look at the initial, kind of painful state of this developer's pet project. The core issue here was a massive disconnect between reality and the codebase itself. Think about a physical book, right? A volume is your top-level container. Volumes absolutely do not have sublevels, but the original code, it actually permitted a generic block header constructor to create a volume at level 2. It's exhausting just thinking about managing that. The code also allowed keyword headers to carry completely irrelevant numerical data. The system was basically handing the developer enough rope to hang themselves by letting pure absurdities compile without a second thought. Moving to Section 2, fixing the block data. Let's see how we match that domain right back to reality.
The fix here was absolutely crucial. The author broke down a generic, catch-all structure into strict, highly specific components. See, the old generic block header tried to do everything all at once. It took a type, an integer level, text, and header info. By ripping out that generic block, we now get specific constructs like block volume, block chapter, and block keyword. Volumes and keywords implicitly sit at level 1 now, so there's no integer field for them at all. Every single constructor only accepts the exact data that is valid for its specific state. You literally cannot create a level 2 volume anymore. The compiler flat out won't let you.
Section 3, removing optional types. Or as I like to call it, goodbye, maybe.
This step brilliantly captures the pure relief of this refactoring. We're fixing the metadata by completely eliminating optional values. Now, in Haskell, optional values often use the maybe type, and the old header info allowed optional fields for just about everything. Talk about a theoretical nightmare. Imagine parsing a numbered header, but theoretically the code said it could be constructed without a prefix, without a number, or without a unit, all because those values were wrapped in maybe. The new strict header info completely strips that out. It guarantees at the type level that every single parsed header has a mandatory prefix, number, and unit. That impossible state of a numberless numbered header, it's just gone.
Now this raises a really interesting question. It's awesome to have clean data structures, for sure. But how does strictly enforcing these types actually change our day-to-day functional parsing logic? Let's find out in Section 4, the shrinking code base. Time to delete some defensive boilerplate. Honestly, this is the most satisfying part of any code makeover, throwing away code you just don't need anymore. Previously, rebuilding a header from that old data structure meant running a gauntlet of tedious defensive steps. You'd have to constantly check if the prefix was nothing. You had to handle the number using fallback functions just in case. You were juggling empty dummy strings constantly. It was defensive programming against states that logically shouldn't have ever been passed into the function to begin with. But look at this shift. Now the developer gets to use beautifully simple direct pattern matching. Because the compiler guarantees every value is present and correct, you don't need any of those paranoid defensive checks. You just ask for the prefix, the number, and the unit, and boom, you get them. Period. The cognitive load drops to near zero because the compiler is doing all the heavy lifting.
You can almost feel the developer exhaling here. This is the parsing function for a keyword header. With the old type signature requiring that generic header info, the dev had to construct this hideous dummy record stuffed with nothings and empty strings just to keep the compiler happy. It was a giant lie. Now, the strict block keyword type takes just a single text value, cleanly returning exactly what it needs. It is now 100% impossible to attach invalid metadata to a keyword header.
Which brings us to Section 5, leveraging the type system. This right here is the big payoff.
So,
What's the ultimate takeaway from this whole refactoring journey? Well, the practical benefits are just massive. The code base shrinks naturally because all that defensive boilerplate is gone. Out go the maybe checks, out go the wildcard pattern matches, and say goodbye to dummy fallback values. But honestly, the biggest win? Fewer unit tests. You don't have to waste your time testing impossible runtime edge cases anymore. Because if it compiles, that entire class of bugs just physically cannot happen.
And beyond just shrinking the code, the domain model now truly mirrors reality. The code's underlying abstract syntax tree perfectly reflects the actual structure of a physical book, with absolutely zero logical gaps. You look at the code, and it's crystal clear. Volumes don't have sublevels, and keyword headers don't have numbers. The code is finally telling the truth about the domain it represents.
Which leads us perfectly to this fantastic realization from the author. It captures the absolute magic of functional programming when you really push the type system. Quote, "The types are now an accurate and self-enforcing documentation." Think about how powerful that is. You don't need to maintain some separate wiki page to remind a new dev that volumes can't have sublevels. The types document it, and they enforce it. That documentation can never go out of date, because if it does, the program literally will not build.
So I'll leave you with this to chew on for your next project. Take a hard look at your own code bases. Are you constantly writing defensive checks for things that shouldn't even be happening? Are you really leveraging your programming language's type system to make your own illegal states unrepresentable? Because if not, well, it might just be time for your own code makeover. Thanks for joining me on this explainer, and keep building smart.